Hey guys, Mr. Betts here. I want to take a look at a variety of examples where we're evaluating antiderivatives using substitution. So let's just jump straight into it. So in a problem like this, the first thing we want to do is we want to choose a value for u. So keep in mind what we're doing here is we're undoing the chain rule, and we essentially have a chain rule type situation going on here because we have a 1 over x function involved and a 2x minus 1 function involved. So we have a function within a function. Keep in mind, we're not taking the derivative of this, so it's not directly using the chain rule, but we're using the chain rule in reverse. So I'm going to make my u choice to be the 2x minus 1 because that would be my inner function if we were doing the chain rule. So I've got u equals 2x minus 1. And by replacing the denominator here with u, then that's going to simplify this expression. This is something we're going to see pretty often if we see multiple terms in the denominator. Choosing u to be the denominator is often going to be a good choice. It's not a steadfast absolute rule, but it's something that will happen pretty often. Then we take the derivative, so du equals 2 dx. Don't forget the dx here. That's absolutely important because we're going to solve this for dx in order to help us get rid of the dx in our expression. So with our choice of u and the derivative of u, and now solved for the differential dx, now I'm going to make my substitution. So we've got the integral, keep the 3 on the top, u goes on the bottom, now instead of the 2x minus 1, and dx is going to become du over 2. Now, simplifying this expression, what I'm going to do is I'm going to take the 3 and the 2, which are both constant multiples. Okay, constant multiples meaning that they're constants that are being multiplied on the inside. So the 3 and the 1/2. And I'm going to take those out front. So we get 3 halves times the antiderivative of 1 over u du. So now, once we've made our substitution, we want to ask ourselves, what do we take the derivative of to get 1 over u? And that's going to be the natural log function. So this is going to be 3 halves times the natural log of u. Keep in mind that u could be a negative value. And when we write the natural log of u, it cannot be negative. So that's why we have absolute values. Also keep in mind that when we take the antiderivative and this symbol goes away, so when we actually take the antiderivative here, the integral symbol goes away and we get our constant of integration. Then the last step here is to rewrite back in terms of the original variable, in this case x. So we have the 3 halves, natural log of the absolute value. Instead of u, we're going to have 2x minus 1 plus c. And a good thing to do when you get an answer like this is to take the derivative of our answer. So take the derivative of this and see if we get back to the integrand that we have in the original problem. I will not do that in this video, but it is a good thing to do and maybe something you could do on your own to confirm our answers. Okay, so second example, I'm going to choose u equals that inner function, natural log of x. Du is going to be 1 over x dx. And so dx is going to be x times du. So making our substitution, we're going to have u to the 3rd power over x. So I'm replacing the natural log that we chose here, and I'm going to replace the dx with x times du. And as long as we've made a good choice for our u, when we take the derivative, we're going to get an expression that's going to cancel out the rest of the x's. So this is going to be the antiderivative of u cubed with respect to u. Then we take the antiderivative. So it's going to be u to the 4th over 4 using the reverse power rule plus c. So when we take the antiderivative, we lose the integral symbol, we get the plus c. And then the last thing we need to do is rewrite it back in terms of the original variable. So the natural log is going back where the u is. So we have the natural log of x to the fourth power over 4 plus c. Third example, this one's a little bit trickier for choosing u. So we want to keep in mind that we're trying to simplify the expression, but also we're going to be taking the derivative of our u, and we want that derivative to be involved in the expression also. So keeping both of those things in mind, I'm going to choose u equals the tangent of x. And just thinking ahead, I know the derivative of tangent of x is secant squared of x. So the derivative part is going to help us get rid of this, and the u part is going to be u squared here. A problem like this might take a little bit of trial and error. This is one of those that where the more experience you have with it, the more practice problems you do, the more comfortable you will be with making that choice. So I'm going to solve this for dx. By the way, I want to mention that this process that I'm taking, you could approach this in several different ways. So you don't have to do this by solving for dx here. One way to do it, and this is a pretty easy example to see what's going on, is that, I made a mistake here. These should be thetas. So in this particular problem, secant squared of theta times d theta is this expression here, which just can directly be replaced with du. This is a general method for doing substitution that will work as long as you make a good choice for u and substitution works. So it's easier to just teach you one way than to teach you several ways. But if you see something like that, you can directly substitute du for this expression here if you want to. So making the substitution, tangent squared is going to be u squared because u is just tangent. The secant squared I'm going to keep there. D theta is going to become du over secant. So in this next example here, this is kind of a tricky one, and this is one where a little bit more experience will make you a little more comfortable choosing your u. So we've got some good choices here. We could say u equals, say, tangent squared of x, theta, sorry. But then du is going to be 2 tangent of theta times secant squared of theta using the chain rule. And that expression right there is not going to really help us with that. So this is not a great choice. We could actually do it with that choice, but we'd have to make some modifications. We could say u equals secant squared of theta. We're going to have the same issues when we take the derivative. We could say u equals tangent of theta. And remember, the derivative of tangent of theta is secant squared of theta, so that's going to be a good choice for us here. We could also say u equals secant of theta, and du is going to be secant of theta times tangent of theta, d theta. And this is something that we could maybe work with, except we're going to have trouble getting rid of this right here. So that's actually not going to work either. So long story short, thinking ahead to what the derivative of my choice of u is going to be, I'm going to choose u equals tangent of theta, so that du equals secant squared of theta, because that's the derivative of tangent, times d theta. And so this secant squared here is going to help us with that secant squared there in the expression. So solving this for d theta, because I want to get rid of the d theta eventually, we get du over secant squared of theta. I do want to point out, and this is a good example to point this out, that this expression, secant squared of theta d theta, is right here. So we could directly substitute du for that because that's right here. I am going to continue doing it the way I have, because doing this is a general method that will always work as long as substitution works and we've made a good choice for u. Okay, so let's make the substitution. Tangent squared is going to become u squared because u is just tangent. I'm going to keep the secant squared of theta in there. D theta is going to become du over secant squared of theta. And as we've seen in previous problems, by making a good choice for u and using its derivative, the thetas are going to go away. So rewriting here, we have the antiderivative of u squared with respect to u. Then taking the antiderivative, we're going to have u cubed over 3 plus c. So when we actually take the antiderivative, the integral symbol goes away, the plus c comes in, and then we replace the u and get our answer. Next problem. So this problem here is, it doesn't look like one that we should have to use substitution. So the first thing I'm going to do is I'm going to rewrite this as cosine of theta over sine of theta with respect to theta. And by writing it this way, we can see now that we have, if we ignore the cosine, we have a function sine of theta within a function 1 over x or 1 over u or whatever. And so this is a good example of one where we can use substitution, but it wasn't obvious from the original presentation of the problem that it was. So I'm going to choose u equals the sine of theta. Like I mentioned in a previous problem, a lot of times the denominator is going to be a good choice for u. That gives us du equals cosine of theta d theta, which is good because that's going to help us get rid of the numerator here. And so d theta is going to be du over cosine of theta. So making the substitution then, we're going to have cosine of theta on top, u on the bottom. D theta becomes du over cosine of theta. And the cosines are going to cancel each other out. And we get the antiderivative of 1 over u with respect to u. Well, what do we take the derivative of to get 1 over u? That's going to be the natural log. So it's the natural log of the absolute value of u plus c. Don't forget the absolute values with those natural log antiderivatives. And then we replace the u with sine of theta. So this is going to be the natural log of the absolute value of sine of theta plus c.